Greetings, welcome back. In the last video, we made these two scatter plots and we created two sets of linear regression output. What are we doing? We are looking at the relationship between the number of bedrooms and monthly rent on an apartment, and we are looking at the number of bathrooms and monthly rent on the apartment. So over here, columns F through N through L, we're examining a model that estimates rent as a function of an intercept and a slope and the number of bedrooms that an apartment has. We're doing the hypothesis test, where our null hypothesis is that our slope beta 1 is equal to 0, that the variables are not related. Number of bedrooms doesn't influence the price of an apartment. And we're going to compare that to the alternative hypothesis, which is simply that beta 1 is not 0, that there is a relationship between bedrooms and rent. So if you change the number of bedrooms, as long as that slope, that beta value is anything but 0, then the rent for that apartment is going to change. We're going to evaluate that null versus alternative hypothesis by looking at the p-value for beta 1, because that p-value tells us the probability that the null hypothesis is true. What's the probability that number of bedrooms and overall rent aren't related? And to tell how strongly the relationship, or how strong the relationship is, we're going to look at the R squared, which is the coefficient of determination, which just tells us what percentage of our outcome variable, rent, can be explained by the model. And since our model only contains number of bedrooms, it basically says what percentage of the variation in monthly rent can be explained by the number of the variation in the number of bedrooms. Boom. Let's take a look at our chart. This is going to beep at me until I tell it to go away. So let's take a look at our scatter plot. On our x-axis, we've got number of bedrooms, and on our y-axis, we've got monthly rent. When we look at this, we can see that there's a pattern, an upward pattern in the dots of the data, meaning that the more bedrooms an apartment has, the higher rent it's likely to receive. Is the relationship perfect? No, because some lie above the line, some lie below, but the data trends upward. Our equation says that rent on an apartment is going to be equal to, let's start with the intercept here, $340.51 for an apartment with 0 bedrooms, which we don't actually have any studios in our data, so we can't extrapolate to say that would be true. But our slope coefficient, 401.1x, that says with each additional bedroom, the price of rent should increase by, on average, $401.10. And with a coefficient of determination, or our R squared, of 0.7406, that tells us that the variation in number of bedrooms, the only variable in this model, explains 74% of the variation in monthly rent. That's a strong relationship. If you know how many bedrooms are in an apartment, you know a lot about how much the rent is going to cost. And if you think about that from your own experience, how much does a 2-bedroom house cost in the place where you live, right? There'll be a small range. So let's jump down to the summary output. If you're thinking, why do we need the summary output when we have that beautiful chart that tells us everything we want to know? Well, the thing is it doesn't tell us everything we want to know. In particular, what it doesn't tell us is the statistical significance. It doesn't do that hypothesis testing part. And our hypothesis test, again, is basically that there is no relationship between the number of beds and the rent on an apartment. We can see from the equation that it appears that each additional apartment adds about $401.10, right? The same number that pops up down here. But is that real, right? Or is that just, could we have gotten that, say by sampling error? So this p-value tells us the probability that this number is really 0 and that those two variables aren't related. And we can see that a p-value of 0.00 means the probability that they aren't related is 0, which means that if we use a 5% statistical significance level, we clear the hurdle because our p-value is less than our 5% cutoff, 0.05. We can conclude that beds are statistically significantly related. We've just done a hypothesis test just by looking at this p-value. So if I were going to sum this up, I'd insert a text box, I'd stick it in here, I would get a little bit particular about my formatting. And I would say the number of bedrooms in an apartment is a strong predictor of the monthly rent. The R squared of 0.7406. See how it matches this one too, R squared 0.7406. Tells us that variation in the number of bedrooms that an apartment has explains 74.06% of the variation in that apartment's rent. Let's go back to the hypothesis test. Our hypothesis test is that null hypothesis is that beta 1 is equal to 0. The alternative hypothesis is that beta 1 is not equal to 0. Our p-value is the probability that the null hypothesis is true. We have a p-value of 0. The p-value of 0.00 indicates that the relationship is significant at the 5% level. It would also be significant at the 1% level. And we can conclude that beds and rent are related, right? We can reject the null hypothesis. You following? Picking up what I'm putting down? Great. So bedrooms and rent related. R squared 0.74 tells us it explains 74% of the variation in rent. And our p-value tells us the relationship is statistically significant. We can reject the null hypothesis, right? Beta 1 is not equal to 0, right? In fact, not only is it not equal to 0, meaning an additional bedroom doesn't raise your rent at all, right? Right. Having an extra bedroom in an apartment should increase rent, on average, by $401.10 per month. Boom. That is our simple linear regression looking at rent as a function of bedrooms. Well, let's pop over and look at bathrooms. Here's our chart. Well, let's just take this. Now we've got a new equation, right? We've got monthly rent and number of bathrooms, and these are separate. So here we're made a model that says that monthly rent is equal to the intercept plus beta 1 multiplied by the number of baths, and our hypothesis test is the same. The null hypothesis is that beta 1 is 0. The alternative hypothesis is that beta 1 is not 0. And as long as beta 1 is not 0, it can be anything. We know that the number of bathrooms in an apartment is statistically significantly related to that rent, because if beta 1 is not equal to 0, any change in the number of bathrooms is going to influence the price of an apartment. Our p-value, again, in this case, is the probability that the null hypothesis is true. It's the probability that the number of bathrooms doesn't influence rent. And the R squared is the coefficient of determination, the proportion of variation in rent that can be explained by the model, which in this case only includes the number of baths as an independent variable. So it tells us the proportion of variation in rent that can be explained by the number of bathrooms. Looking at our chart, we have number of bathrooms on the x-axis and monthly rent on the y-axis, and again, we've got an upward sloping line. The R squared of 0.5291, our coefficient of determination, tells us that bathrooms explain about 52% in the variation in the price of monthly rent. Not as strong as bedrooms. Variation in bedrooms explains more. The slope, 378.43, tells us that each additional bathroom gets us about $378 rent more, if that's the only thing in our model, and that an apartment with no bathrooms should be about $560.67. Again, we don't have any data with no bathrooms, so that would be extrapolation, and we can't conclude that that would be true. But let's take a look at our output. What do we have? We've got an R squared of 53, or 52.91, and it matches that on our chart. Because it's a simple linear regression, it will. And we can scroll down here and say, with regard to bathrooms, that the p-value is 0.00, otherwise known as less than 0.05, which is the cutoff we've given ourselves to determine whether or not it's statistically significant. It says 1% there, but it said 5% on the first video, so we're sticking with 5%. But it would be statistically significant at the 1% level too. So, with the p-value of 0.00, we would say that the probability that a house with 10 bathrooms would have the same rent as a house with 1 bathroom, that's 0. A house with more bathrooms is going to have a higher rent. In fact, for each additional bathroom, we would think that rent would go up by about $378.43 on average. The number of bathrooms is statistically significantly related to rent on an apartment. So let's take this chance and summarize it. And we're going to add a little bit to this summary too, because now what we can do is we can take a look. Is the price of an apartment related to the number of bedrooms? Yes. Is it related to the number of bathrooms? Yes. But the relationship between number of bedrooms and rent is stronger, as indicated by the R squared. An R squared of 0.7406 tells us that the number of bedrooms explains 74% of the variation in the price of rent, whereas bathrooms explains only 52%. So, number of bedrooms is a stronger predictor. But let's not leave number of bathrooms out in the lurch. Let's give it its own nicely formatted text box. Text box. I used all of my space last time, so let's just start with using all my space. And let's try this for an explanation. There is a statistically significant relationship between the number of bathrooms in an apartment and its rent. At the 5% level, we can reject the null hypothesis that beta 1 is 0. The coefficient of determination of 0.5291 tells us the number of bathrooms in an apartment explains about 52.91% of variation in rents. This is lower than the R squared on the model. Why can we just say it's lower than the R squared for the model containing bedrooms as the independent variable. 0.7406, 0.7406, meaning that the number of bedrooms in an apartment is a better predictor of rent amount than is the number of bathrooms, right? We could also rephrase this if we wanted to by saying that the relationship between bathrooms and rent is not as strong as the relationship between bedrooms and rent. When bathrooms is the only independent variable, so why am I saying this? Where bathrooms is the only independent variable in the model, it's because bathrooms is going to be so correlated with number of bedrooms. It's going to be correlated with square footage. So I think that when we move on to our multiple regression model, we'll find that this number drops, because if we include bedrooms in there, adding an additional bathroom is only so useful if you have more bedrooms, right? So when bathrooms is the only independent variable model, we can interpret the model as one additional bathroom in an apartment will raise rent on average, of course, by $378.43 per month. Boom. Zooming out. Trying to zoom out, not zooming out. We can see that we've essentially created two simple linear regression models. We've compared their coefficient of determination to see which one is a stronger predictor of rent. And we've, can't do that, hold on. Sorry, I got distracted. My formatting, you know I can't handle it. And we've completed two hypothesis tests, which are asking essentially if the independent variables, bedrooms, bathrooms, are statistically significant to the price of rent for that given apartment. And we've concluded both times, yes, they are. With p-values of 0, the probability that they're unrelated is 0. All right, so bedrooms, more rent, more bathrooms, more rent. Bedrooms explain 74%, bathrooms explains 52%. All right, we're going to come back and tackle the multiple linear regression version of the same problem. Because now that we understand how each of these variables affect the price of an apartment individually, we can combine them and see how they affect separately. Okay, see you in a minute.